Hello, class 12th physics, chapter atoms, बोर्स postulate. पहले हम बोर्स postulates की बात करेंगे, फिर बोर्स हाइड्रोजन एटम देखेंगे और फिर हाइड्रोजन स्पेक्ट्रम सीरीज को डिस्कस करेंगे. ऑलराइट, सो बोर्स postulates, ये 3 postulates हैं जिन्हें मैं लिस्ट डाउन कर रहा हूँ. So first postulate is stationary orbit postulate. While orbiting around nucleus, electron does not radiate energy. So it has a constant energy and it revolves around the nucleus. No radiation of energy takes place in this process. And thus these orbits are called non-radiating orbits or stationary orbits. So quantization of energy level, second postulate. Electron can revolve around nucleus in only those orbits for which its angular momentum is integral multiple of h upon 2 pi. H is Planck's constant. So what does it mean, angular momentum? We know it is mvr. We will put subscript nn for nth orbit, that is equal to nh upon 2 pi, and n is 1, 2 and up to so on, up to infinity. So this is the quantization condition. So electron can not be anywhere in the around the nucleus, but it can have only those values for which its angular momentum is integral multiple of h upon 2 pi. H is Planck's constant. So remember one thing, this angular momentum has unit same as Planck's constant, unit of Planck's constant, that is joule second or kg meter square per second. Well, next, third postulate can be explain the origin of a spectrum. So here I have written this heading: energy emission during transition. What is transition? When electrons jumps from lower energies to higher energies, lower energy levels to higher energy levels, or vice versa. So we can write that when an electron gains energy, it jumps to higher energy level which is temporary for it. So it returns back by emitting energy in the form of photon equal to the energy difference between the energy levels. आप इसे डायरेक्टली ये लिख सकते हैं कि जब इलेक्ट्रॉन हायर एनर्जी लेवल से लोअर एनर्जी लेवल में आता है, मैंने यहाँ पूरा प्रोसेस बता दिया कि इलेक्ट्रॉन ऊपर जाएगा ही क्यों. ऐसा नहीं है कि कोई भी ये इलेक्ट्रॉन किसी ऑर्बिट में था और उससे अपने आप नीचे आ जाएगा, ऐसा नहीं। पहले वो नीचे की ऑर्बिट से ऊपर जाएगा और तब नीचे आएगा। सो व्हेन एन इलेक्ट्रॉन गेन्स एनर्जी, एनर्जी गेन करने के बाद जब जंप करके ऊपर जाता है, विच इज टेम्परेरी, ऊपर जब वो गया है तो वो टेम्परेरी एनर्जी लेवल है उसके लिए, वो उसके लिए अलाउड नहीं है। सो इट रिटर्न बैक बाय एमिटिंग, और जब वो वापस आता है तो इट एमिट्स सम एनर्जी इन द फॉर्म ऑफ फोटोन। जो हमारे इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम सीरीज है उसकी किसी वेव की फॉर्म में वो एनर्जी को एमिट करेगा, और वो जो एनर्जी होगी वो एनर्जी लेवल्स जो हैं उनके एनर्जी के डिफरेंस के बराबर होगा। सो इफ देयर आर टू एनर्जी लेवल्स, दिस इज n1, this is n2, so it has returned to from n2 to n1, so it is emitting a photon of energy E. So that E is equal to E2 minus E1. And if in terms of h nu equal to h nu, because we are talking about the energy of emitted photons, which is h nu, so it is E2 minus E1. So nu is equal to E2 minus E1 upon h. And if in terms of wavelength, nu is c by lambda, so it is E2 minus E1 upon h. So lambda will be equal to, in fact not needed to make formula for lambda, I'm setting it for 1 upon lambda. It will be E2 minus E1 upon hc. So this is what Bohr's model all about. Now this is the time to apply Bohr's postulate to hydrogen atom. So this is Bohr's hydrogen atom, or Bohr's theory for hydrogen atom, or with the help of hydrogen atom, derivation of velocity of electron, orbiting electron, radius of orbit, and energy of electron in an energy level, or energy of energy level. So these are the heading, but I will prefer Bohr's hydrogen atom. So first we will draw hydrogen atom. Hydrogen atom is the simplest atom. It has one proton. That proton has charge Qp, charge of proton, which is equal to plus E. And electron is orbiting around it. For this electron, there are many energy levels. So let us suppose right now it is at nth energy level, which has radius Rn. This is that electron having charge Qe, which is equal to minus E. It has mass m and it has velocity Vn. Velocity of electron in nth energy level. So force, centripetal force for circular motion is provided by electrostatic force between electron and proton. So Fc is equal to Fe. What is Fc? mv square upon r. Subscript 1 upon 4 pi epsilon naught. This is Coulomb force. 1 upon 4 pi epsilon naught. I am writing it simply K. Q1 is E, Q2 is E. We will not put that negative sign because we are dealing with force. Upon R square, so Rn square, where K is 1 upon 4 pi epsilon naught. Epsilon naught is permittivity of free space. So next step, r will get cancelled. It will be mv subscript n square equal to ke square upon rn, equation 1. Now I'll continuously put equation 1, 2, 3 and so on. Now cross multiply it. It will be mvn square rn equal to ke square. Yeah, need to put equation 2. Now according to Bohr's quantization postulate, so its quantization postulate, always remember its angular momentum mvr is equal to nh upon 2 pi. This is equation 3. Now divide equation 2 by equation 3. So we will have mv square r upon mv r, that is equal to ke square upon nh upon 2 pi. Oh, sorry for that, it has gone out of focus. So now focus here. All right, so everything else will get cancelled here. We will have vn remaining here, and on other side it will go into numerator 2 pi ke square upon nh. This is also an equation, so we'll put this as equation 4. And also remember, just memorize this formula, or try to do this derivation very fast, because this formula can be asked in the exam, so you need to be quick. And other than that, for numerical purpose, you need to remember only this: Vn is inversely proportional to quantum number of orbit. But actually this is the velocity of orbiting electron. But what after it? Next is putting this value of v from equation 4 to equation 3. From 4 and 3. So what we will do, equation 3 is mvr, so m in place of v, will put that value of v, which is 2 pi ke square upon nh, and rn is equal to nh upon 2 pi. So it looks like they will get cancelled, but no, they are not getting cancelled. So rn is equal to n square h square upon 4 pi square ke square m. See, many terms are there, and it is very possible that you might do some mistakes here. So this is equation 5, and see, once again you need to be very quick to derive these, because sometimes direct question can be asked, and I don't think that it is a wise decision to spend more time on this. So now remember, for numerical purpose this is enough, but for otherwise you have to remember this, or need to derive it fast. So now just hold on. Next is, so what we can do here, for this step we can put a heading: velocity of orbiting electron. and here we can put radius of electron orbit. Next thing is energy. So energy of orbiting electron or energy of electron energy level. So what can we do here? That energy will comprise, it will be kinetic energy plus potential energy. So what is kinetic energy here? Alright, so we'll do some rough work. So EK, that is kinetic energy, will be half mvn square, and we have already this mv square value in equation 1. So we can directly put the value here, ke square upon Rn. So it is half ke square upon Rn. Next is potential energy Eu. That is, see, potential energy is k q1 q2 upon R, and k q1 is E, q2 is minus E. This time I am putting minus. Earlier that was force. In force we don't put positive or negative, but here it is energy, we put positive negative. So this is minus ke square upon Rn. So this is half of ke square upon Rn. This is 1 of ke square upon Rn. Looks similar. So that is why En will be equal to half ke square upon Rn minus 1, purposely I am writing 1, ke square upon Rn. Now half minus 1 is minus half ke square upon Rn. Now see, here we can just by comparison draw a conclusion that if we know the value of let us suppose En, if En is minus x, then Ek, same value in positive, will be plus x, and potential energy will have double that value. So this is minus 2x. Such kind of numerical can come. So remember this interrelation between them in your mind. Now what we will do, here we have equation 6, and we will put the value of 5 here in 6. So we will have 1 by 2 ke square upon the value of Rn is n square h square upon 4 pi square k square m, and 2 2s are 4, it will go up, don't give up, minus 2 pi square, it is going up, k square, it is going up, e to the power 4 m upon n square h square. So finally what happens actually if we put numeric value, I'll move to next page. So En is equal to minus 2 pi square k square e to the power 4 m. You should remember this also. That is why I am asking you to be quick. Alright, so here now I can lead it to two different ways. One in which we can put numeric values here, convert it will come out to be in terms of joule, but convert that into electron volt. So it will be minus 13.6 upon n square electron volt. That is a direct thing. But here, what other thing we can do? We can 2 pi square k square e to the power 4 m. We can multiply hc here, and now leave this hc, leave this n square, and rest of other is Rydberg constant, rhc upon n square. So where r is called Rydberg constant, and h and c, Planck's constant and speed of light. So in these two ways this energy expression can be expressed, and on the basis of this we can say that ultimately, first thing, it is negative, so electron is bounded with nucleus system, and En is inversely proportional to n square. So remember these things. And next there will be hydrogen spectrum series. So here is this R is 1.097 something into 10 to the power 7 per meter. So actually most of the time this value is not given in the exams, and if you people want to go through this way, you should remember this value. Most of the time I haven't seen that they have given this value of Rydberg constant. Anyway, so here, okay, and why its unit is meter inverse, so you will come to know about it a little later. So okay, once again a quick summary. So far what we have done, we have found out the formula for speed of electron in nth orbit, Vn, and which is equal to 2 pi, you can see in your previous notes, ke square upon nh. It's not working. And in the same way, we have this radius Rn is equal to n square h square upon 4 pi square ke square m. And now we have this En, and which is minus 13.6 upon n square electron volt, and also it is minus rhc upon n square. Now if we talk about the ground state means first energy level. N equal to 1, then V1 is equal to 2 pi k e square upon h. So what I'm doing nothing new. I'm doing, it is just the fundamental of I'm putting n equal to 1, 2, 3. So for ground state it is 1. So we are just following the fundamental of mathematics. और ये आपकी ग्राउंड स्टेट की एनर्जी, ग्राउंड स्टेट की वेलोसिटी हो गई. In the same way, there is nothing much interesting about this. और इसकी एक वैल्यू होती है 5 × 10⁻⁷ समथिंग. तो that velocity, in fact, bit greater than that, and in the order of speed of light, 10⁶ or 7. That is pretty close to speed of light. Anyway, we are interested in this R1, which is equal to h square upon 4 pi square k e square m. We can put the value of k here, 1/4 pi epsilon naught, and we can further simplify this r, and this is for ground state, and it is called Bohr radius. So for ground state energy level, radius of ground state energy level is Bohr radius, and in the same way here, the ground state E1 equal to minus 13.6 electron volt, or simply minus RHC. So this is the discussion about its ground state, and further we will proceed accordingly. So now till now we have proceed like this. Then it was, and now we ended up here, but the story is not over yet. Now the thing is, if electron makes some transition, I mean that Bohr's hydrogen atom is over now, but in order to explain its spectrum, what we will do, we will go for the third Bohr's postulate, and according to third Bohr's postulate, electron transition, if electron transition takes place, then the emitted photon, the energy emitted in the form of photon, and that is equal to the difference between two energy levels. Now we will use this to explain the origin of a spectrum. So expression for energy emitted by hydrogen atom during electron transition, or origin of hydrogen spectrum. So now what we will say that as we did earlier, so now I am just going into main point, that an excited electron while returning to ground state, ground or lower states, emits energy in the form of photon. Having energy equal to energy difference between two energy levels. That is, E is equal to E2 or E final. E2 is much better. E2 minus E1, because final initial in which way we are looking at, so that makes confusion. Okay, so this is level 1, this is level 2, so it was in this level, and while returning to 1 it has emitted a photon of energy E. Now here E2 is actually minus 13.6 upon, it can be, and actually E2 is not exactly second energy level, it is something higher energy level. So don't get confused that I'm not going to put 2 square here. As far as its expression is concerned, so the expression contains the term n square, and often we look at this, so yeah, this can be a confusion. So what I am doing, I am putting it n1 and it n2. So now this will be a bit problematic for you people, because I am putting subscript and subscript, n2 n1, so subscript on subscript, so it is En2 is actually 13.6 N2 square electron volt. Or in terms of Rydberg constant, minus RHC upon N2 square. And what about N1? It is 13.6 upon N1 square in electron volt, and N1 square in terms of RHC. So now onward I am going to use this RHC expression to set a proper value to derive a proper expression for radiant energy. So now, according to Bohr's third postulate, energy of photon emitted photon E equal to E2 minus E1. So E equal to, right now I am writing it E, but it is actually h nu. It is energy of photon. It is energy of an electromagnetic wave. So E2 minus RHC upon N2 square minus RHC upon N1 square. So we will take RHC common, and this will become positive, so it will be written like this, and this will be 1 upon N2 square. Most of the student will get confused, but I want to tell you that it is positive now, so I have written it in forward and it in backward. so don't get confused about it. Next, all right, so next I will go to next page actually. All right, so now this is the expression for emitted energy, but if we put, since E equal to h nu, where nu is the frequency of emitted radiation, so h nu is equal to RHC 1 upon n1 square minus 1 upon n2 square. We can cancel h both side, so here we will get expression for emitted frequency, which is nu equal to RC 1 upon n1 square minus 1 upon n2 square. And one more thing, well, if you don't want to go like that, okay, still in the same expression we can put E equal to hc by lambda, or what you can do, put nu equal to c by lambda. So in both ways, here this expression you should put here, and here this expression you should put here. So well, it was our main equation. So yeah, I am putting this here also. So it is, so this is one of the expression, just remember this also, but this one is important, more important than this. RHC 1 upon n1 square minus 1 upon n2 square. HC will get cancelled, so it will be 1 upon lambda equal to R 1 upon n1 square minus 1 upon n2 square. So all right, so side by side I will, okay, this is for nu, this is for lambda. It is also exhausted. Now for different set of n1 and n2, different spectrum lines are formed. So keeping that thing in mind, I am dividing this page into 5 categories. 1, 2, I think that will look good. Five categories in which actually there are huge number of transitions, but we will select 5 out of them. They are important. First one, if n1 is 1, that is the energy level in which excited electron is returning is the ground state, and n2 is anything above 1, then this spectrum lies falls in Lyman series. This is called Lyman. One upon one. I'm purposely writing it 1 upon 1 square upon minus 1 upon n2 square, and keeping in mind n2 has values greater than 1. It is 2, 3, 4 and so on. So this is Lyman series. Now n2 equal to 2. So if while returning it the excited electron, n1 is 2, while returning it falls into second energy level, then it forms this series. N2 is anything greater than 2, then we form Bohr series. Is equal to R 1 upon 2 square minus 1 upon n2 square. Remember, this n2 and this n2, they are not equal. A condition is put on that. Now, if n1 is 3, means it returns at third energy level, n2 is greater than 3, then 1 upon lambda, it is Paschen series. And if n1 is 4 and n2 is greater than 4, then it is bracket series. Bracket, double T is there. So it is not tough. It looks very complicated, but it is not tough. See how easily we can write these expression. So last one is fund. Many people call it fund and many other call it puffund. It is fund. R 1 upon phi square minus 1 upon n2 square. So this Lyman series lies in UV region, this in visible, this one in infrared, near infrared, infrared, far infrared, this one also infrared, far infrared. We will not say extremely far, it is near, but rest of other are far. And remember, visible region, we know that this is the order of decreasing frequency or increasing wavelength. So it means visible, VIBGYOR. That is why after this it is infrared, infra, away from that red, and ultraviolet, before violet, that is ultraviolet. So Bohr series lies in VIBGYOR region. This can be testified also, and yeah, this question is asked in the exam, that what is the shortest wavelength of Lyman series and all that. But before that, we can draw these transition here. All right, no need to view it from here. So I'm drawing some energy levels. This is n equal to 1, more gap, n equal to 2, bit lesser gap. This is what it is symbolic representation all about. Just in order to highlight the inner ones. And all right, so after so many transition, there is n equal to infinite. So all right, so first transition, if it is coming from some higher energy level and falling into first, then it forms Lyman series. This is Lyman series. And in second, it is Balmer series. So okay, in third, Paschen series. So I am drawing three lines. They can be infinite lines from any of the higher level till here. Any of the higher level till here. So Lyman, Balmer, Paschen. Next is bracket. And last one is Fund. Oh, only two member I can draw here. Okay, so now the question is asked that what is the longest wavelength for Lyman and what is the shortest wavelength for Lyman? So now remember one thing. Okay, there can be a transition from infinite in every case. So there are always two transition. One is from just next or energy level and other is from infinite level. So when gap is large, when this gap is large, En2 minus En1, this gap is large, then the energy of emitted photon will also be large, and we know that E equal to h nu, it will also be large. That is, nu will have large values, greater values, and we know nu equal to c by lambda, so lambda will have smaller values. In the same way, if this gap is small, then emitted energy will also small, nu will also small, and lambda will be large. So for shorter wavelength in Lyman, okay, one category. For shortest wavelength or for longest wavelength, all right, so in Lyman, shortest wavelength will be obtained. Shortest wavelength, smaller value, when transition takes place from large gap. energy gap is very large. It means it will release more energy and frequency will be high. Frequency will be high means wavelength will be smaller. So we need large gap. For shortest wavelength we need large gap, and this large gap in Lyman can be obtained if transition takes place from infinite to 1. So for Lyman series, shortest wavelength can be obtained. Okay, we know that n1 is 1, but for shortest wavelength n2 should be infinite. So also in each case, longest can be only shortest wavelength can have value only when transition takes place from infinite to that level. So that's why for Bohr n1 equal to 2 we know, but n2 equal to infinite. Paschen bracket Bohr bracket, it is looking like barium and bromine. Anyway, n1 equal to 4, n2 equal to infinite. And Fund PF, Paschen and Fund, n1 equal to 5, n2 equal to infinite. And for longest wavelength, nu should be small, e should be small, means this gap should be small. It means just next energy level. For Lyman, n1 equal to 1, n2 equal to 2. Here n1 equal to 2, n2 equal to 3. n1 equal to 3, n2 equal to 4. n1 equal to 4, n2 equal to 5. n1 equal to 5, n2 equal to 6. And that's all. This is how we can calculate longest and shortest wavelength in different series, just keeping this idea, this picture in mind. See, no need to memorize it, just go through this analysis. For shortest wavelength, what are our requirement? Shortest, if lambda is short, smaller, nu will be large, then E will be large. So for Lyman series, the expression is expression for wavelength okay, keeping in mind that n2 is greater than 1. So for shortest wavelength, as we have discussed earlier, that for shortest wavelength, if wavelength is short, frequency is large, energy is large, so gap is large. That is, it will come from infinity, and here we have listed out also. For shortest wavelength, each time, just memorize this thing. For shortest wavelength, n2 is infinity. n2 infinity. So here 1 upon lambda Lyman shortest equal to r, 1 upon 1 square minus 1 upon infinite. No need to put square, but I am putting it. So it is r. So lambda Lyman shortest is equal to 1 upon r. I'm not going to calculate right now. I'm just writing it in the form of an expression only. Now for longest So just reverse this order. For longest wavelength, lambda is large, so frequency is less, so energy is less, so gap is less. Gap is less means from just next energy level it will fall into it. So N2 is equal to 2 just next. So 1 upon lambda Lyman longest is equal to R 1 upon 1 square minus 1 upon 2 square. So if we solve this longest, this will 1 by 4, so after solving it will be 3 by 4. So lambda Lyman longest is equal to R by 4 by 3R. Well, this 1 by R is we'll do some rough work, actually not required, but still 1 upon 1.097 into 10 to the power 7, so it will be approximately 0.99, maybe one step, but it will close to 0.99. It will go up 10 to the power minus 7 meter. And remember, it is in meter, that is why Rydberg constant is in meter inverse. So well, if we shift decimal here, it will be -8, so that lies in ultraviolet region. Here now we have a trick. We will multiply 4 by 3 into this one, 0.99 into 10 to the power minus 7. This will be approximately 1.33, and so final answer will be approximately 1.3 something like that into 10 to the power minus 7 meter. Next is Bohr. Okay, so for Bohr shortest, okay, Bohr first its expression 1 upon lambda equal to R 1 upon 2 square minus 1 upon n2 square. Now for shortest, n2 equal to infinity. Just remember this thing, just mug up this thing. So Bohr, so 1 upon lambda Bohr shortest is equal to R 1 by 2 square, as I used to write, minus 1 upon infinity square. So it is R by 4. So lambda shortest is 4 by R, and as we calculated earlier, that value of R is 1 upon R is, this is 4 into 1 upon R, so value of 1 upon R is 0.99 into 10 to the power minus 7, so it will be somewhere about 3.9, I guess. It will be close to this value into 10 to the power minus 7 meter. So actually it is close to 4, and this is what the range of visible spectrum. So if we talk about its color, so it will be violet. Shortest in the visible region. Now for longest, n2 equal to just next, so that is 3. So 1 upon lambda Balmer longest is equal to r 1 upon 2 square minus 1 upon 3 square. So this is r 1 upon 4 minus 1 upon 9. This is r 36, 9 minus 4, that is 5. Actually, I don't want to go into unnecessary calculations, so I skip those. So it is 36 by 5r, that is 36 by 5 into 1 by r, and that is 36 by 5 into 1 by r is this 0.99. Actually, significant figures you can calculate it up to 3, and I probably think that 0.994 I think it is. So anyway, you can exactly calculate it. I'm giving you a rough idea for this. 10 to the power minus 7, so it will be 7.2 multiplied by this, approximately 7.1 into 10 to the power minus 7 meter, and which is red. Next is Paschen. So for this lambda Paschen actually 1 upon 3 square minus 1 upon n2 square. So shortest n2 equal to infinity, so 1 upon lambda Paschen shortest equal to r 1 upon 3 square minus 1 upon infinite. So lambda Paschen will be equal to 9 by r, that is 9 into 0.99 into 10 to the power minus 7. So it will be about close to 8 point something, 8.9 something into 10 to the power minus 7 meter, which is infrared region. Now no need to explain about that. Okay, and longest n2 is equal to 4. So 1 upon lambda Paschen longest is equal to r 1 upon 3 square minus 1 upon 4 square. So this is 3 9 4 4 16 9 144 and 7. So lambda 144 upon 7r, so this is approximately 20. So 20 into 0.99 into 10 to the power minus 7. So it will be about approximately 2 into 10 to the power minus 6 meter. In the same way, bracket 1 upon lambda bracket is equal to r 1 upon 4 square minus 1 upon n2 square. So in this way, shortest n2 equal to infinite, longest n2 equal to, I'm directly doing it now, 5. So 1 upon lambda shortest equal to r 1 by 4 square minus 1 by infinity square, that is 0. So it will be r by 16. So lambda BRS equal to 16 by r, that is 16 into 0.99 into 10 to the power minus 7, which is close to, now I'm rounding it off to 1. So 16 10 to the power minus 7 meter, and in order of magnitude it will be 1.6. Scientific notation, it will be like this. And for longest, BRL, it will be R 1 by 4 square minus 1 by 5 square. So 16 and 20. 16 and 20, 250, 150, 500, 400 actually, 400, and 9. So lambda BRL is equal to 400 upon 9 into R, which is this is close to approximately 44 into 0.99 into 10 to the power minus 7, which is close to 4.3, actually 43, I'm rounding it, 43, and shift decimal place here, so it will be 10 to the power minus 6 meter. And last one is Fund. So for that, for that 1 upon lambda Fund is equal to r 1 upon 5 square minus 1 upon n2 square. So for shortest, n2 is equal to infinity, so 1 upon lambda Fund shortest is equal to r 1 upon 5 square minus 1 upon infinity square, so that is r by 25. So lambda Fund shortest is equal to 25 by r, which is 25 into 0.99 into 10 to the power minus 7 meter, which is close to 2.5 into 10 to the power minus 6 meter. And for longest, n2 is equal to 6, so 1 upon lambda pf longest is r 1 upon 5 square minus 1 upon 6 square, so that is about 911. So 1 upon lambda 900 upon 11 r, so approximately it is about 82. I'm just now taking a rough assumption. sorry, I have reciprocated it, so it is now lambda. I have reciprocated, so lambda fund longest 82 into 0.99 into 10 to the power minus 7 meter, that is 8.2 into 10 to the power minus 6 meter. This is how this spectrum goes. And this is all about hydrogen spectrum. And now in next section we will talk about excitation potential